Imagine you're standing somewhere in East Africa, maybe 74,000 years ago. It's morning, but the sun looks wrong, dim, filtered, like you're seeing it through smoke, except there's no fire nearby. The light has a strange flat quality that makes everything feel distant and muted. Then you notice the ash, tiny grey flakes drifting down like snow, except you've never seen snow. They settle on your skin, on the leaves, on the water. They keep coming, hour after hour, day after day. The animals sense it too. Birds go quiet. Herds move restlessly, spooked by something they can't see. Something invisible has changed the world, and nothing will be quite the same again. What you don't know, what you can't possibly know, is that 5,000 miles to the east, the Earth has just torn itself apart. On an island that will one day be called Sumatra, a supervolcano has detonated with a force almost beyond comprehension. The largest explosive eruption in 25 million years. Enough material ejected into the atmosphere to bury all of South Asia under a blanket of ash. Enough sulfur launched into the stratosphere to dim the sun across half the planet. The blast left behind a crater so massive it now holds a lake 100 kilometers long, and according to some scientists it nearly killed every last one of us. The claim sounds almost absurd, that humanity, our entire species, was reduced to maybe 2,000 survivors, that we came within a few thousand individuals of vanishing forever, that the eruption of a single mountain rewrote our DNA in ways we're still discovering today. But here's what makes this story so fascinating. The truth turns out to be even stranger and more layered than that headline suggests. Because when you start digging into what really happened 74,000 years ago, you find yourself on a journey through 3 different timescales. The hours and days of the eruption itself, ash and darkness spreading across a continent, the centuries and millennia of climate chaos that followed or maybe didn't, depending on which evidence you trust. And finally, the deep time written in our genes, bottlenecks and crashes and expansions stretching back not just 74,000 years, but nearly 1 million. If you're listening to this to fall asleep, that's exactly why I make these. So maybe subscribe and tell me, where are you right now and what time is it? I love checking the comments. It's like Berlin at breakfast and Boston at bedtime, all of us scattered across the world contemplating this one shared ancestral story. The Toba supervolcano is real. The eruption happened. The ash is still there, buried in layers across 2 continents. But did it really bring humanity to the brink of extinction? Did 2,000 survivors huddle in some unknown refuge while the rest of the world froze? Or is the story more complicated, more interesting, and ultimately more hopeful than we first thought? Let's go back, way back, to the day the sky went dark. Before we get to the eruption, before we watch the mountain explode and the ash fall, we need to understand what kind of world it was falling into. Because 74,000 years ago, Earth was already a challenging place to be human. This wasn't some Eden interrupted by catastrophe. This was a planet deep in the grip of an ice age, where survival was never guaranteed, and small populations were always just one bad season away from disaster. The technical term is marine isotope stage 4. The transition from MIS5A into 4 had just occurred, meaning the planet was sliding into a colder phase. Ice sheets that had retreated during warmer periods were advancing again across the northern hemisphere. In North America, glaciers were spreading south from Canada. In Europe, ice was creeping down from Scandinavia. These weren't just snowfields. These were walls of ice sometimes 2 miles thick, grinding continents beneath their weight, locking up so much water that global sea levels had dropped somewhere around 80 meters below where they are today. Think about what that means. Coastlines you know from maps didn't exist. Where there's now open ocean between mainland Asia and Indonesia, there was land. The Sunda Shelf was exposed, connecting what we now call Thailand, Malaysia, Sumatra, Java and Borneo into a single enormous peninsula. Australia and New Guinea were joined as Sahul. Britain was still attached to Europe. The world's geography was fundamentally different. You could walk to places that now require boats. This exposed continental shelf wasn't wasteland either. These were productive environments, river valleys and coastal plains and forests that supported substantial populations of animals, and probably humans too. Populations that now drowned, their archaeological sites buried under 100 meters of seawater. When we talk about how many humans existed 74,000 years ago, we're reading a record with whole chapters missing. Entire regions where people might have lived are now underwater, inaccessible, invisible to us. So who were these humans? If you could somehow take a census of Earth in 74,000 BC, what would you find? Homo sapiens had been around for something like 200,000 years by this point, maybe longer depending on how you define the species. Early modern humans with anatomy basically indistinguishable from ours. But we were still a relatively modest, geographically limited group. Most of the human population was in Africa, scattered across the savannas and woodlands and forest edges, wherever resources could support small bands. There had been earlier attempts to expand beyond Africa. During wetter periods in the preceding tens of thousands of years, Homo sapiens groups had pushed into the Levant, into Arabia during green phases when monsoons turned deserts into grasslands. But many of these early expansions seem to have failed, populations contracting back or disappearing entirely when climates shifted. By 74,000 years ago, we probably weren't very numerous outside Africa. Maybe some small pioneering groups clinging to southern Asian coastlines, maybe populations scattered across the Middle East, but nothing like the global dominance that was still millennia in the future. And we weren't alone. This is crucial to understand. The planet in 74,000 BC was home to multiple human species, all competing for resources, all adapted to different environments. In Europe and Western Asia, you had Neanderthals, robust and cold-adapted, master hunters of Ice Age megafauna. In Eastern Asia, there were Denisovans, known mostly from genetic traces but clearly successful across enormous territories. On the Indonesian island of Flores, there was Homo floresiensis, the so-called hobbit people, a diminutive species that had survived in isolation for tens of thousands of years. Our species was just one player among several, not yet dominant, not yet inevitable. The climate itself was volatile in ways that are hard to appreciate from our relatively stable modern perspective. This wasn't just a steady cold period. The late Pleistocene was characterized by what scientists call Dansgaard-Oeschger events, abrupt climate oscillations that could swing temperatures in the northern hemisphere by several degrees in just decades. These weren't gradual changes. These were whiplash shifts driven by changes in ocean circulation and ice sheet dynamics. Monsoons would strengthen and weaken. Rainfall patterns would shift. Entire ecosystems would transform within a human lifetime. The world was already testing us, already pushing human populations to adapt, migrate, or die. The stage was set for catastrophe. And then the mountain exploded. The mountain that was about to reshape human history didn't appear overnight. Toba was the product of a geological process that had been building for millions of years, a consequence of Earth's restless crust grinding against itself in slow motion. Picture the floor of the Indian Ocean, hundreds of kilometers south of Sumatra. The Indo-Australian tectonic plate is moving northeast at roughly 6 or 7 centimeters per year. Not fast by human standards, but relentless. And it's not sliding past the edge of Southeast Asia. It's diving underneath it, plunging down beneath the Sunda plate in what geologists call a subduction zone. One piece of Earth's crust literally sinking beneath another, descending into the hot mantle below. As that oceanic crust descends, something crucial happens. It's not just rock down there. It's rock that's been sitting on the ocean floor for millions of years, saturated with seawater, carrying hydrated minerals down into the depths. And when that water-rich rock gets dragged down to depths of 100-150 kilometers, where temperatures reach 1,000 degrees Celsius, the water does something remarkable. It lowers the melting point of the surrounding mantle rock. Suddenly, rock that should still be solid begins to melt. Magma forms, and because it's less dense than the solid rock around it, it starts rising. Slowly at first, percolating upward through fractures and weak zones in the crust. As it rises, it accumulates, pools, forming vast chambers of molten rock kilometers beneath the surface. This is how the Sunda volcanic arc formed, the chain of volcanoes stretching along Sumatra and Java, and Toba sits right in the middle of it. But Toba wasn't just another volcano. The magma-feeding Toba was special, or perhaps we should say dangerous. As magma rises and sits in crustal chambers, it evolves. The first minerals to crystallize out tend to be dense, iron-rich compounds that sink. What remains becomes increasingly enriched in silicon, aluminum, and dissolved gases. The magma becomes rhyolitic, thick and viscous like cold honey. And crucially, it becomes loaded with water vapor and carbon dioxide, gases dissolved under immense pressure. This is the recipe for catastrophic eruptions. Basaltic magma, the kind that feeds Hawaiian volcanoes, is fluid. It flows relatively easily, releasing gases gradually. When it erupts, you get lava fountains and flows, dramatic but manageable. Rhyolitic magma is different. It's so viscous that gases can't escape easily. Pressure builds and builds until eventually the rock can't contain it anymore. Beneath Toba, geophysical imaging suggests there wasn't just one magma chamber. There was a complex system, a stack of what scientists call magma sills or lenses, pancake-shaped bodies of molten rock spread across an area 10 or 20 kilometers wide, sitting at various depths between 7 and 30 kilometers beneath what is now Samosir Island in the middle of Lake Toba. At the top of this system, in a relatively shallow chamber just a few kilometers down, the most evolved, gas-rich, explosive magma was accumulating, and it had time, hundreds of thousands of years. Because Toba had done this before, the geological record shows at least 4 major caldera-forming eruptions at Toba. The first, the Harangal Dasiti eruption, happened roughly 1.2 million years ago. Then came the oldest Toba tuff around 840,000 years ago. The middle Toba tuff followed about 500,000 years ago. Each time, enormous volumes of magma erupted explosively. Each time the overlying crust collapsed into the emptied chamber, forming a caldera, a volcanic depression miles across. Each time the landscape of northern Sumatra was reshaped, buried under thick blankets of volcanic deposits. These weren't small events. The oldest Toba eruption alone probably ejected something like 2,000 to 2,500 cubic kilometers of material. That's already larger than any eruption in recorded human history. But they were just rehearsals. By 74,000 years ago, the magma system beneath Toba had been recharging for 500,000 years since the last major eruption. Fresh magma rising from below. Existing chambers crystallizing, differentiating, becoming more evolved. The shallow reservoir accumulating a catastrophic volume of rhyolitic melt, superheated, gas-saturated, building pressure against the relatively thin roof of overlying rock. The numbers, when you finally see them laid out, are almost incomprehensible. The youngest Toba eruption ejected somewhere between 2,800 and 3,200 cubic kilometers of dense rock equivalent material. Dense rock equivalent is important because it accounts for the fact that pumice is full of bubbles. When scientists talk about eruption volumes, They're estimating what the volume would be if you compressed all that frothy pumice back down into solid rock. The actual volume of material as it came out was even larger. Let's try to make that scale tangible. Mount St. Helens in 1980 ejected about 1 cubic kilometre. The eruption that decapitated the mountain, that sent ash across multiple states, that became one of the most iconic volcanic events in American history, was 1 cubic kilometre. Krakatoa in 1883, the eruption that killed tens of thousands and was heard thousands of miles away, ejected roughly 25 cubic kilometres. Tambora in 1815, which caused the year without a summer and probably killed more people than any other volcanic eruption in recorded history, released about 160 cubic kilometres. Toba was 2,800 to 3,200, 20 times Tambora, more than 100 times Krakatoa. If you could somehow take all the material Toba ejected and spread it evenly across the entire United Kingdom, you'd bury the country under roughly 13 metres of rock. Over 40 feet of volcanic deposits covering an area the size of a small nation. And the eruption mechanism itself was the stuff of planetary nightmares. When the pressure finally exceeded the strength of the overlying rock, the mountain didn't just erupt, it exploded. The eruption column punched through the troposphere, through the stratosphere, reaching heights probably exceeding 40 kilometres, higher than most commercial jets fly, high enough that ejected material entered the stratospheric winds that circle the planet. As enormous volumes of magma emptied from the chamber, the roof collapsed. Not gradually, catastrophically. Thousands of cubic kilometres of rock dropping hundreds of metres, maybe kilometres, into the void. The surface above didn't just sink, it fragmented, shattered, creating a caldera roughly 100 kilometres long and 30 kilometres wide, one of the largest volcanic depressions on Earth. The column collapse generated pyroclastic flows, avalanches of superheated gas and pulverized rock, moving at speeds that might have exceeded 300 kilometres per hour. These weren't just hot. They were hundreds of degrees Celsius, incinerating everything in their path, flowing across the landscape like liquid, but faster and far more destructive. Near the vent, these flows deposited ignimbrate sheets, welded volcanic rock hundreds of meters thick in places, and the ash went everywhere. Carried by high-altitude winds, Toba ash has been found in sediment cores from the South China Sea, from the Indian Ocean, from ice cores in Greenland. A geological signature of a single catastrophic day that would be readable in Earth's rock record for millions of years. The volcano was ready, the planet was vulnerable, and the clock was running out. Nobody alive 74,000 years ago could have known what was coming. No written records, no seismographs, no emergency broadcasts, just the Earth itself, beginning to send signals that something fundamental was about to break. The first warnings probably came weeks, maybe months before, earthquakes, not the catastrophic shaking that would come later, but persistent tremors, the kind that make water ripple in containers, that wake people at night. Magma pushing upward, fracturing rock, forcing its way toward the surface. Animals might have sensed it first, behaving strangely, migrating away from areas they'd inhabited for generations, hot springs getting hotter, fumaroles opening in the ground, venting sulphurous steam. Then, maybe days before the main event, the earthquakes intensified. Ground that had been solid for thousands of years began heaving, cracking, trees toppling, rock slides cascading down slopes. Anyone living within sight of the mountain would have known something was terribly wrong, but there was nowhere to go, no frame of reference for what was building beneath their feet. When it finally began, probably sometime in the hours just before dawn, the initial blasts were phreatic. Groundwater, superheated by rising magma, flashing instantly to steam. The pressure building until rock shattered, sending columns of steam and pulverized stone thousands of meters into the air. These weren't the main event. They were the mountain's way of clearing its throat. Within hours, maybe minutes after those first blasts, the magma reached the surface, and the character of the eruption changed completely. Now it wasn't just steam. It was molten rock, gas-charged, exploding upward with a violence that probably registered on seismographs that wouldn't be invented for another 73,000 years. The Plinian column, a roaring pillar of ash and gas and pulverized pumice, climbing at speeds that might have approached the speed of sound in the lower atmosphere. 30 kilometers up, 35, 40 kilometers, punching through the stratosphere. At that altitude, there's almost no weather. The ash wasn't being carried by local winds anymore. It was entering the planetary circulation system, the jet streams that would distribute it across continents. Below the rising column, the scenario was already apocalyptic. The eruption was so violent, ejecting material at such rates that the volcanic edifice couldn't structurally support what was happening. The ground began collapsing, not gradually, in catastrophic pulses, thousands of cubic kilometers of overlying rock dropping into the emptying magma chamber, fragmenting, mixing with erupting magma, generating pyroclastic density currents that defied imagination. These flows weren't lava. They were avalanches of superheated gas and rock fragments, moving like fluid but deadly in ways that fluid isn't. Temperatures inside the flows probably exceeded 400, maybe 500 degrees Celsius, hot enough to carbonize wood instantly, hot enough to melt glass, and they moved fast. Computer models suggest velocities of 200 to 300 kilometers per hour, maybe faster in the initial surges. Everything in their path simply ceased to exist. Forests incinerated in seconds, rivers boiled away, the flows coursed down valleys, across lowlands, extending tens, possibly hundreds of kilometers from the eruption center. Some probably reached the Indian Ocean to the west, the Strait of Malacca to the east. Eyewitnesses, if any survived at sufficient distance, would have seen glowing avalanches of destruction expanding outward like the shock wave from an explosion, which, in a sense, is exactly what they were. The ignimbrite sheets they deposited are still there today, buried beneath vegetation and soil. Near the caldera, deposits hundreds of meters thick. Further out, tens of meters. Layers of welded volcanic glass and pumice that cooled so slowly they partially crystallized, creating what geologists call tuff, compressed volcanic rock that in places forms cliffs and mountainsides across northern Sumatra. But the truly planetary scale destruction was just beginning. The ash column, now 40 kilometers high, was spreading laterally. At those altitudes, it encountered stratospheric winds capable of carrying particles around the world. Within days, maybe a week, Toba ash was falling across South Asia, across the Indian subcontinent, across islands in the Indian Ocean. Fine grey powder drifting down from darkened skies like snow, except it didn't melt. It accumulated. Sites in India have been found with youngest tuba tuff layers 10 to 15 centimeters thick. That's 6 inches of volcanic ash, thousands of kilometers from the eruption. In Malaysia and parts of Indonesia closer to the source, deposits measured in meters. The ash blanketed an estimated 7 million square kilometers of land and ocean. Roughly 7 or 8% of Earth's entire surface covered in a geological instant. Imagine you're part of a small band of early humans somewhere on the Indian subcontinent, Homo sapiens or perhaps late archaic humans, living in a world already marginal, already cold because you're in the grip of a glacial period. You've never heard of volcanoes. You have no concept that the Earth itself can explode. One morning, the sun doesn't rise properly. There's light, but it's wrong. Dim. The sky has a grey cast that doesn't clear. By midday you realise the sun itself looks pale, distant, like you're seeing it through smoke, but there's no fire. Then the ash starts falling. At first just a dusting easy to brush off, but it keeps coming, day after day, coating leaves, choking water sources, getting into food, making people cough. Plants that were green start turning brown. Animals grow thin, confused, their food sources disappearing beneath the grey blanket. You have no framework for understanding that an explosion happened on an island thousands of kilometres away. No way to know that what you're experiencing is ash fallout from the largest volcanic eruption your species would ever witness. All you know is that the world is ending, and you don't know why. But even the ash wasn't the worst part. The eruption had injected enormous quantities of sulfur dioxide into the stratosphere. Estimates vary, but we're talking about hundreds of millions of tons, possibly billions. At stratospheric altitudes, sulfur dioxide reacts with water vapor to form sulfuric acid aerosols, tiny droplets that remain suspended for years, forming a global veil that reflects incoming sunlight back into space. This is the mechanism of volcanic winter, not the ash, which settles relatively quickly, the aerosols. For months, maybe years after the eruption, the planet's surface received measurably less sunlight. Temperatures dropped. How much is still debated. The cooling might have been several degrees in some regions, less in others, but even a few degrees sustained over years would be catastrophic for ecosystems already stressed by Ice Age conditions. And 9 to 14 days after it began, the main eruptive phase finally exhausted itself. The magma chamber, drained of its most volatile gas-rich melt, could no longer sustain the column. The eruption sputtered, diminished, stopped. What remained was a hole in the earth, a caldera 100 kilometers long and 30 kilometers wide, a wound in the planet's crust that would eventually fill with water, creating Lake Toba, today one of the largest and most beautiful volcanic lakes on Earth. Serene, peaceful, surrounded by lush tropical forests, a popular tourist destination where people swim and fish and take photographs of stunning sunsets over calm water. You would never know, looking at it today, that this tranquil lake sits inside the scar of an explosion that changed the course of human history. That beneath that placid surface lies a volcanic system that could, given enough time, do it all again. But 74,000 years ago, in the immediate aftermath, there was no lake yet, just a smoking crater and a world going dark. In 1998, an anthropologist named Stanley Ambrose sat with the pieces of a puzzle spread out before him. On one side, geology, evidence that 74,000 years ago, Toba didn't just erupt, it detonated with a force almost beyond measurement. On the other side, genetics, the strange fact that modern humans, for all our numbers and variety, are surprisingly alike under the skin, less genetically diverse in many measures than chimpanzees or gorillas or orangutans with far smaller ranges. Ambrose's idea was simple and terrifying. What if those two facts were connected? What if, when Toba blew, it almost erased us? The mechanism he proposed felt elegant, almost inevitable. Toba injects vast amounts of sulfur dioxide high into the stratosphere. There, where weather barely reaches, the gas reacts with water vapor, forming an invisible veil of sulfuric acid droplets. Not big raindrops, but particles so fine they can hang in the upper atmosphere for years. Those particles do one main thing very well. They bounce sunlight back into space. If you've heard of the year without a summer after Tambora erupted in 1815, you've seen a small version of this. Crops failed across Europe. Frosts came in June. Skies turned a milky, unsettling white. But Tambora was tiny compared to Toba. Ambrose argued that if a VAI-8 super eruption like Toba could loft enough sulfur that high, the result wouldn't just be a bad year. It could be 6 to 10 years of cold, dimmed light, a volcanic winter, Early climate models backed up the possibility. Some simulations suggested global temperatures might fall 3 to 5 degrees Celsius. A world already in an ice age, shoved a step deeper into the cold. In some regions, especially continental interiors or high latitudes, the modelled cooling was even harsher. 10, maybe 15 degrees colder, at least for a while. The kind of drop that doesn't just chill evenings. It restructures ecosystems. Less sunlight means less photosynthesis. Trees grow slowly, or not at all. Grasses fail to sprout on schedule. In the oceans, tiny photosynthetic plankton struggle, dimming the base of the marine food web. The effect doesn't have to be absolute to be devastating. A 20% drop in plant productivity, sustained over years, can echo upward through every level of life. Herbivores find less to eat. Their numbers fall. Predators that depend on them grow thin, desperate, then disappear. For human hunter-gatherers, exquisitely tuned to the seasonal movements of animals and plants, the world itself seems to stop keeping its promises. Migrations fail. Rivers freeze earlier. Fruits don't ripen when they should. The familiar calendar of survival breaks. In the Toba catastrophe picture, that's exactly what happened. Ash and aerosols dim the sun. Temperatures fall. Rainfall patterns shift. Across Africa and Asia, already cool, dry landscapes tip into something harsher. Not everywhere, not equally, but in enough places that human populations, already small, begin to fracture. Some bands perish outright, caught in regions where plant and animal life simply can't keep up with the combined stress of ice age and volcanic winter. Others retreat into refugia, small pockets where local conditions remain just tolerable enough. Maybe along coasts where the ocean moderates the climate. Maybe in deep river valleys or near persistent springs and wetlands, places where a little greenery clings to life. In this view, Homo sapiens doesn't glide smoothly through the late Pleistocene. It stumbles, it crashes. A global population of perhaps hundreds of thousands, still modest by modern standards, shrinks rapidly to only a few thousand souls. Ambrose spoke cautiously of a few thousand survivors. Popular science took that phrase and gave it an edge. 10,000, 3,000, 2,000, 1,000 breeding pairs. Different retellings chose different numbers, but the message was the same. We almost didn't make it. To understand what that would mean for our DNA, imagine a glass jar filled with marbles, tens of thousands of them, in hundreds of subtly different colours. Each colour is a genetic variant, a slightly different version of a gene, or a small stretch of DNA. This is your species before the catastrophe. Rich, varied, every colour a possibility. Now tilt the jar and let almost all the marbles fall away. Earthquakes of hunger and cold shaking the jar decade after decade. At the end you scoop up a small handful that happened, by sheer luck, to remain. Maybe it's 3,000 marbles, maybe 10,000, maybe only 2,000. However many it is, your handful doesn't carry all the colours from the original jar. Some shades are gone forever. Others are suddenly common, not because they were better, but because they were in the right place at the right time. Every marble you add in the future, every descendant born from that moment on, must be drawn from the colours in that reduced handful. This is a genetic bottleneck, a narrowing of the passage through which all future diversity must flow. When geneticists first began to read human DNA at scale, they saw something that looked very much like the aftermath of such a narrow passage. Compared to chimpanzees, whose populations had been divided and reunited many times across Central Africa, humans looked strangely uniform. Most of our genetic variation was shallow. Different, yes, but not deeply diverged. Analyses using tools like coalescent theory suggested that, at some point in the late Pleistocene, the effective size of our breeding population had dipped to only a few thousand individuals. Ambrose's hypothesis fit perfectly into that gap. Here was a documented planetary-scale event, precisely dated to around 74,000 years ago. Here was a genetic signal hinting at small ancestral populations somewhere in the same broad window of time. It was irresistibly tempting to draw a straight line between them. Toba explodes, the sky darkens, temperatures fall, ecosystems reel, humans nearly vanish. Our genetic diversity plummets, squeezed through a bottleneck of a few thousand survivors in scattered refuges. And from that remnant, every person alive today descends. It's easy to see why this narrative caught fire. It had everything. A single, spectacular geological event, a global climate disaster, a razor's edge escape from extinction, and perhaps most appealing of all, it offered a clean, cinematic explanation for a messy scientific observation. Why you and a stranger on the far side of the world are, at the molecular level, such close cousins. The story spread quickly. It appeared in books and magazine articles, in television specials about supervolcanoes, in lectures where professors would tell students that at one point maybe only 2,000 of our ancestors huddled under darkened skies, the fate of the species resting on their fragile shoulders. The numbers varied from telling to telling, but the image stayed fixed. A tiny band of humans standing at the edge of an abyss carved by a Sumatran volcano. And like many compelling stories, it lingered. It wove itself into the way people thought about human uniqueness, about our shared vulnerability, about the stroke of luck or misfortune that could have erased us before history even began. But science is a restless thing. As new data accumulated from lake sediments in Africa, from ice cores, from more detailed genetic studies, the neatness of the Toba catastrophe picture began to fray. The classic theory, with its brutal volcanic winter and its handful of survivors, would not go unchallenged. To see why, we have to look again at the evidence, at what the rocks, the climate, and our own DNA really say about 74,000 years ago. If you want to test a story about global catastrophe, you don't start with myths or memories. You start with mud. Picture a long, slender cylinder of lake sediment, lifted slowly from the bottom of an East African lake, layer upon layer, year upon year, like pages in a book that has been quietly writing itself for tens of thousands of years. Dust from distant deserts, pollen from trees on the shore, tiny fragments of charcoal from ancient fires, silica bodies from grasses and reeds, phytoliths, each one a microscopic fingerprint of the plant it came from. Somewhere in that stack of layers there should be a moment when the sky went dark. At Lake Malawi, a deep rift lake in East Africa, scientists have that book in their hands. When they scan down through the layers, they find what they were looking for, a thin but unmistakable band of volcanic ash. Chemically it matches Toba. The fallout of that Sumatran super-eruption, carried halfway across the world and gently settling onto the water surface. On the catastrophe picture, everything below that ash is the before world. Everything above it is after. If Ambrose's volcanic winter happened as imagined, years of dimmed sunlight, collapsed ecosystems, mass die-offs, then this is where the story should twist. Below the ash, one pattern. Above it, something utterly different. But that's not what the mud says. The phytoliths continue, almost as if nothing has happened. Grasses, woodland plants, the mix of vegetation around Lake Malawi shifts. Yes, but not abruptly. No sudden wholesale replacement of forest with barren ground. No decade-long absence of plant productivity. The charcoal fragments, the tiny signatures of ancient fires, tell a similar story. The fire regime before and after the ash looks continuous. People, lightning and dry seasons were still lighting landscapes on fire at much the same pace. There is a line of ash in the core, a silent record of an eruption that shook half the planet. But the lake's ecology doesn't seem to crash. In this part of Africa, at least, there is no sign of a prolonged brutal volcanic winter, and this matters because East Africa is not just any backdrop. It is one of the main homelands of early Homo sapiens. If Toba had plunged our species to the brink, you might expect to see its fingerprints here. Shrinking woodlands, altered grasslands, a break in the familiar dance of plants and fire. Instead, the record looks strangely calm. Shift your attention thousands of kilometers away to the Indian subcontinent. Here, the Toba ash isn't just a whisper in lake mud. In places, it lies on the ground in thick blankets, meters deep in ancient landscapes. If humans lived here before the eruption and died out in its wake, their traces should be interrupted. Tools below, emptiness above, or a different culture stepping into the gap. At sites like Jwalapuram, in what is now the Kurnool district of India, archaeologists have been patiently peeling back those layers. They find stone tools, flaked points, scrapers, cores, embedded in sediments that were once open ground. Above those sediments, the Toba ash, a distinct, pale band. Above the ash, more tools. When researchers compare the technology below and above that dividing line, a pattern emerges. It looks familiar. The way flakes are struck from cores, the shapes of points and scrapers. The overall signature of the toolkit remains remarkably similar across the ash. There is no dramatic collapse into cruder technology, no long hiatus where people vanish, then later reappear with a wholly different way of making tools. It looks, instead, like continuity. Like some group of hominins, perhaps early Homo sapiens, perhaps closely related cousins, were living there before Toba, saw the ash fall, endured whatever followed, and kept on napping stone much as they had before. That doesn't mean the eruption was a non-event in India. Local environments could still have been harshly disrupted. Ashfall can choke rivers, smother plants, force people to move. Populations might have dropped or shifted without leaving a clean break in the stone record. But the image of India emptied of humans, then slowly repopulated from some distant refuge, no longer fits well with what the ground is showing us. While archaeologists and geologists were reading these quiet lines of continuity, climate scientists were revisiting the other half of the picture, the sky. Early models of Toba's impact treated it as a scaled-up version of known eruptions, injecting enormous amounts of sulfur high into the stratosphere and keeping it there. The result on the computer screen was a planet plunged into years of deep cold. But as models improved, higher resolution, better physics for aerosols, more realistic data from recent eruptions like Pinatubo and Tambora, the numbers began to shift. Sulfur yield, particle size, how droplets clump together and settle out. These details turned out to matter immensely. Tiny changes in assumptions produced big differences in the modelled climate response. Some newer simulations still show significant cooling, global average temperatures dropping a degree or two. In the coldest regions, especially in the northern hemisphere, more than that, but the duration looks shorter, often a few years of strong anomalies, not a frozen decade that remakes every ecosystem on Earth. Most models now show a world that is knocked hard, but then recovers toward its previous state on human rather than geological timescales. And importantly, the cooling is not uniform. High latitudes in the north, already sitting under Ice Age conditions, take a heavy hit. Some simulations show parts of Asia and Europe becoming even more hostile, with longer winters and altered rainfall. But closer to the equator, especially in the tropics of the southern hemisphere, the signal is often muted. In some Antarctic records, the response to Toba is surprisingly subtle or even ambiguous. When you overlay that patchwork of modelled climate impacts with what we know about where humans were, a picture starts to form. At 74,000 years ago, our species was still primarily African, with small or transient populations reaching into Western and Southern Asia. If East Africa and other tropical refuges were partially buffered, still dimmer, still cooler, but not catastrophically so, then the heartlands of Homo sapiens may have escaped the worst of the volcanic winter. None of this exonerates Toba. The eruption was enormous. The ash reached across continents. The sulfur aerosols did change the climate, at least for a while. The immediate region around Sumatra would have been devastated. Local populations, human and non-human, would have faced horrors that don't easily fit into numbers or models. What is changing is not our sense that something big happened, but our confidence about what that something meant for our species as a whole. The strongest version of the catastrophe theory, the one where Toba single-handedly drives humans down to a mere 2,000 or 3,000 survivors, now looks, in the light of lake cores, stone tools, and refined climate models, more like a compelling story than a firmly established fact. When geneticists look at our DNA today, they do see signs that, in the past, our population was small. They see bottlenecks, dips, constrictions in the flow of genetic variation, but those signals are smeared out over time. They don't come stamped with labels saying caused by Toba or caused by Ice Age drought. When you line up the finest-grained genetic reconstructions with the precise timing of the Toba eruption, the match isn't as tight as people once assumed. The few thousand effective breeders that models infer for some periods of our history might not correspond to a sudden crash at 74,000 years ago at all. They might reflect a long period of being rare and scattered, or multiple smaller bottlenecks in different regions at different times, or earlier crises that predate Toba by hundreds of thousands of years. In other words, the jar of marbles was never as full as we imagined, and the hand that shook it may not have belonged to a single volcano. The more closely scientists read the evidence, the more the simple Toba story begins to blur. The eruption was real. The ash fell. Temperatures dipped. Some places must have suffered terribly. But the idea that the entire human species was pushed through a razor-thin bottleneck by that one event alone, that we all descend from a tiny band of Toba winter survivors, is no longer the only, or even the most likely explanation, which leaves a deeper mystery. If Toba did not almost erase us, why are we so genetically uniform? Where did the signal of near extinction come from? To answer that, we have to look past the dramatic, well-dated scar of a single super eruption and down into older, darker layers of our past, into a time when our ancestors weren't yet fully human as we know it, and when the world itself was in the grip of a far more protracted crisis. To understand that older, darker history, you have to do something strange. You have to take living people, right now, breathing and blinking under electric lights, and treat them as fossils, not fossils in stone, fossils in code. Imagine you could line up every copy of a particular gene from people all over the world. Every version of that stretch of DNA, from your cells, from mine, from a herder in East Africa and a fisher in the Philippines, from someone in Iceland and someone in the Amazon. Some of those gene copies would look almost identical. Others would differ at a few letters. A handful would be quite distinct, shaped by long histories in different corners of the planet. Now, instead of reading the code from left to right, imagine reading it backward in time. Every difference between two copies of a gene is like a tiny tick mark, created by a mutation in some ancestor long ago. The more differences there are, the further back you have to go to find the moment when those two copies were still one and the same, sitting in the chromosomes of a single person. Geneticists call that moment the coalescent, the point where two lineages merge into a common ancestor. If you trace all the versions of a gene in the world today back through their little trees of ancestry, something interesting happens. Branches keep fusing as you go deeper in time. 10 copies become 5 lines, 5 become 3, 3 become 1. Do that not just for the one gene, but for thousands scattered across the genome, and a pattern starts to emerge. When populations are large, with many people passing on their genes, these trees stay bushy. Lineages take a long time to merge. There are many different branches coexisting side by side, and you have to go far back before they meet. When populations are small, with fewer individuals breeding, the trees close in on themselves. Lineages coalesce quickly. They bump into the same ancestors over and over, because there just weren't many people alive to choose from. This is the essence of coalescent theory. You look at the way genealogical branches fold together as you walk back in time, and from that folding pattern, you infer how wide or narrow the river of ancestors must have been. If the branches stay wide and separate for a long stretch of time, that suggests a big population. If they collapse into a few common ancestors very suddenly, that suggests a bottleneck. It sounds abstract, almost like a math puzzle, but this is what modern population genetics rests on. Every mutation, every shared stretch of DNA you carry is a tiny timestamp. Add enough timestamps together, and you can sketch the rise and fall of populations that lived hundreds of thousands of years before anyone learned to write. But there's a wrinkle. When geneticists talk about the size of past populations, they don't usually mean how many humans were alive on Earth that day. They talk about something slipperier, effective population size. Effective population size, usually written as NE, is the size of an imaginary, perfectly well-mixed, perfectly random mating population that would give you the same pattern of genetic drift you see in the real world. In that perfect imaginary population, every individual has the same chance to reproduce. Sex ratios are even. There's no long-term structure, no isolated valleys or favoured lineages. Real populations are nothing like that. Some people have many children, others have none. In some times and places, far more women than men leave descendants, or the other way around. Groups split and merge, migrate and isolate. Wars, famines, cultural rules about marriage and kinship. All of these skew who passes on genes and who does not. All of those skews shrink knee. The result is that effective population size is usually smaller, sometimes much smaller, than the actual head count. For many species, NE can be a 10th, a 20th, even less of the census size. A wild population of 50,000 animals might behave genetically like an idealized population of just 5,000. A human population spread across a continent might number in the hundreds of thousands, yet have an effective size of only tens of thousands. So when you hear a number like 2,000 survivors, or 1,280 breeding individuals, what the genetics is really whispering is subtler. At this point in time, the ancestors of living humans, taken together, behaved, genetically, as if there were only about this many idealized breeders. The real number of living bodies could have been significantly higher, perhaps several times higher, and even that 2,000 comes with fuzziness. Assumptions about mutation rates, generation lengths, how structured those ancient populations were, change the assumptions, and the number bends. Still, even with those caveats, the story in our DNA is striking. In 2011, 2 researchers, Heng Li and Richard Durbin, took the coalescent idea and pushed it in a new direction. Instead of just looking at differences among many people, they asked, how much history can you recover from a single whole genome? Their method, with the calm technical name PSMC, pairwise sequentially Markovian coalescent, slides along one person's DNA, region by region, reading how often the 2 copies of each segment, the one from the mother and the one from the father, seem to share recent or ancient common ancestors. From the density of mutations and the way these ancestries cluster, The method reconstructs a rough timeline of effective population sizes, like a cardiogram of a species' heartbeat. When Lee and Durbin ran this on human genomes, they did not see a simple flat line with one enormous dip at exactly 74,000 years ago. They saw something more complicated. Long stretches where knee hovered in the tens of thousands, gradual rises and falls, evidence of contractions and expansions, but not a single sharp worldwide plunge that neatly lined up with Toba's eruption. Different human genomes told slightly different stories. African lineages especially preserved deeper, more complex patterns, consistent with multiple subpopulations within Africa, splitting and mixing over long periods. Non-African genomes showed a clearer, more recent constriction, one that matched something else we know from archaeology and fossils. Around 60,000 to 70,000 years ago, a branch of our species left Africa for good. That movement, small in numbers at first, enormous in consequence, left a crisp signature in our DNA. Most people living today outside Africa trace a large fraction of their ancestry back to a relatively small group of migrants from a larger African population. That is a bottleneck. Not necessarily a brush with extinction, but a founder event. A few lineages stepping into a vast new world of empty territory. As those migrants spread through Arabia, into Eurasia, down the coasts of South Asia, into Australia and beyond, their descendants carried only a subset of the genetic variation that existed back home. Outside Africa, genetic diversity is lower, and the telltale patterns of coalescence lineages collapsing back into a small number of ancestors are stronger. This out-of-Africa bottleneck is one of the most robust findings in human genetics. It fits with fossils, with stone tools, with dates from multiple lines of evidence. But it is not the same thing as the Toba catastrophe. It does not require that the entire human species was reduced to a few thousand people, huddled in a single refuge by volcanic winter. It only requires that a subset of that species, a small river branching off the main channel, carried our lineage into the rest of the world. So why then do we, as a species, have such low genetic diversity compared to our close cousins, the other great apes? Chimpanzees and bonobos, even some gorilla populations, show more genetic variation across their range than all humans on Earth put together. It's as if they carry thicker bundles of ancestral threads, more tangled and diverse, while ours are a thinner, more uniform skein. Part of the answer seems to be that our effective population size has been modest for a long time. Even before the out-of-Africa journey, our ancestors may have lived in relatively small, scattered groups, rarely reaching the global numbers you might imagine. Part of it lies in structure. For much of our history, Africa itself seems to have hosted multiple semi-separate populations of early Homo sapiens and closely related forms. These groups would sometimes mix and sometimes drift apart, their genes weaving in and out like channels of a braided river. From the perspective of any one channel, the total flow looks smaller than the whole, and part of it is that our past is not a single bottleneck, but several. Local crises, climate swings, founder events when small bands pushed into new territories, each one shaving away a little variation here, a little there. On top of all this, natural selection itself can erode diversity in certain regions of the genome, especially where beneficial mutations have swept through populations or where harmful ones are pruned away over and over. That pruning can make our genetic forest look sparser than it truly was in terms of simple head counts. If you picture human history as a river, it's tempting to look for one giant concrete dam, a single disaster like Toba, squeezing the flow down to a trickle. But when geneticists read our DNA, they see something different. They see a river that narrows and widens many times, long, shallow constrictions where numbers were low but not vanishing, sudden tight narrows where only a few lineages squeeze through, a migration here, a regional drought there, side channels splitting off and carrying people into new lands, some drying up, others rejoining the main flow. What reaches the present is not a clean, straight line, but the combined result of every bend and every bottleneck. Every time our ancestors were few, and every time they were many. Toba may have been one rock in that river, one obstacle that deflected and disturbed the flow, but the low diversity we see today, the whispers of near misses with extinction, seem to come from something older, deeper, more prolonged than one eruption 74,000 years ago. To find that story, you have to follow the river much further upstream, into a time before Homo sapiens, when our ancestors were fewer than we ever imagined, and the world itself was caught in a crisis that lasted not for years, but for tens of thousands of years. The story surfaced in 2023, quietly, in the pages of a technical genetics paper. No exploding volcanoes, no ash beds you can dig with a shovel, just numbers. The researchers used a new tool with the oddly gentle name FitCoal, Fast Infinitesimal Time Coalescent. Under the hood, it's a more finely toothed version of the methods we just talked about. Instead of reading one long, blurry cardiogram of population size, it slices time into many tiny steps and asks at each step, how wide was the river of ancestors here? They fed it thousands of modern human genomes from around the world, African, non-African, many different populations. They asked the model to trace all those branching lineages backward through time, letting them fuse and vanish and reappear in the most likely way. And when they followed the lines not just back 100,000 years, or 200,000, but almost 1,000,000 years into the past, the river did something shocking. It didn't just narrow, it nearly disappeared. According to their reconstruction, sometime around 930,000 years ago, the effective size of our ancestral population plunged. Not from tens of thousands to a few thousand, the way you might expect from an ordinary rough patch, but to around 1,280 breeding individuals, and then it stayed there. Not for a bad decade or a bad century, but for something like 117,000 years. From about 930,000 to 813,000 years ago, the main line of ancestry that would eventually lead to us seems to have passed through an eye of the needle, a long drawn-out bottleneck where, generation after generation, there were only enough effective breeders to fill a large village. If you run the numbers the way the authors did, that implies the loss of about 98, maybe 99% of the prior population. Ancestral Homo, our great-great-great-grandparents in the broadest sense, reduced to a sliver of what they'd been. Now, remember what 1,280 really means. That's an effective population size, an NE, not a head count. The real number of living bodies could easily have been several times higher. A few thousand, maybe tens of thousands scattered across a continent, babies born and dying, groups splitting and joining, a patchwork of valleys, coastlines and refuges. But whatever the exact census, the genetic behavior of that whole ancestral network, who actually passed genes down through the bottleneck to us, looked as if only about 1,280 idealized individuals were doing the breeding. From our perspective, hundreds of thousands of years later, it's as if almost every branch of the family tree was pruned away, leaving just a few thin twigs to carry on. And these weren't Homo sapiens yet. Our species, as far as we can tell from the fossils, doesn't show up until around 300,000 to 350,000 years ago. Skulls and faces from places like Jebel Irhoud in Morocco look recognizably human. Flat faces, smaller brow ridges, though their brain cases still hold on to a more archaic shape. The bottleneck FitCoal picks up is more than 500,000 years older than that. It doesn't squeeze modern humans. It squeezes the population that would someday give rise to us, to Neanderthals, and to our shadowy cousins the Denisovans, a stem group of ancestral Homo standing at a crossroads of evolution, suddenly reduced to a tiny remnant. What could have done that? Here, genetics hands the story off to climate. Between about 1.25 million and 700,000 years ago, Earth's ice ages changed their rhythm. Before this point, glacial cycles were relatively short and gentle, waxing and waning every 41,000 years, paced by regular shifts in the tilt of Earth's axis. During what geologists call the mid-Pleistocene transition, that pattern broke. The ice ages stretched, deepened, became more erratic. Instead of many shallow glaciations, the planet slipped into a new mode of fewer but much more severe ice ages on roughly 100,000-year cycles. Ice sheets grew larger. Cold snaps lasted longer. The whole system of winds, currents, and rainfall that feeds life on land and sea began to lurch and stutter. For ancestral humans living in Africa and nearby regions, that likely meant repeated waves of cooling and drying, grasslands shrinking, forests contracting into green islands, lakes dropping, rivers becoming seasonal trickles or vanishing entirely. You can picture it as continents of habitat fracturing into archipelagos, patches of land where life could hang on, separated by widening deserts and hostile terrain. In such a world, big continuous populations splinter. A widespread lineage of early Homo might find itself breaking into small scattered groups, each huddled around whatever resources remained. Some would vanish when their patch failed. Others would persist stubbornly in hidden refuges, along persistent lakes, on cool uplands, in pockets where local geography defied the larger trend. If you link that picture with the Fit-Col results, a possible story emerges. The ancestors of all later humans may have been pushed into a small number of such refuges, their total effective breeding population shrinking to something like 1,280 for a very long time. Groups waxing and waning, meta-populations rising and falling, but overall numbers never climbing back to their previous heights until the worst of the climatic instability eased. From our vantage point nearly 1 million years later, the implications are staggering. Every human alive today, everyone you know, everyone you've heard of, everyone who ever lived within our species, appears to be descended from a population that, for over 100,000 years, was smaller than many modern towns. Walk through a city of 100,000 people, and then try to imagine a world where the entire future of our lineage rested in the hands of a few thousand scattered ancestors. Children playing by shrinking water holes, adults scanning the horizon for game that no longer came, elders remembering a time when the rains were more reliable and the world felt wider. Their survival, through those brutal, fluctuating millennia, is the reason you're here to listen to this story. But how confident can we be? Not everyone is convinced that the bottleneck was as sharp or as prolonged as the Fit-Col model suggests. Some geneticists point out that the method assumes a simplified kind of population, well mixed, more or less uniform through time. Real ancient humans probably lived in a much more complex pattern, many semi-isolated groups, mixing occasionally, splitting often, maybe even interbreeding with other now extinct hominins we haven't yet found in the fossil record. That kind of structure can sometimes mimic the genetic signature of a bottleneck. Imagine dozens of small bands spread over a continent, each with their own quirks and histories. Over time, one subset of those bands might, by chance and geography, contribute more to the ancestry of living humans. Others might leave no surviving descendants at all. From the perspective of our genomes today, it could look like a sudden global crash, even if, on the ground back then, there were many more people alive in total, just arranged in complicated ways. There's also the simple fact that fossils from around 900,000 years ago are sparse. We don't yet see a clean, obvious extinction and replacement pattern in the bones to match the sharp dip in the genes. That doesn't mean it didn't happen, only that the physical record is thin, and the debate is very much alive. So the 1,280 figure, like the famous 2,000 survivors attached to Toba, should be read as an estimate, not a census. A way of saying, sometime in this window, the ancestors of living humans went through a period of very low effective numbers. Whether that means a literal handful of small breeding groups hanging on by their fingernails, or a more braided, structured set of populations that only behaves, in retrospect, as if it were that tiny, is still being argued. What's clear, though, is that if you're looking for a moment in our deep past that fits the idea of a near extinction, a time when the human line contracted to something on the order of a village and stayed there for longer than Homo sapiens has even existed, you don't find it at 74,000 years ago. You find it much further back, near 900,000 years ago, in a world none of our species ever saw. In that sense, the haunting line often repeated about Toba, that only about 2,000 humans survived, may be pointing at the wrong disaster, in the wrong era. There may indeed have been a time when our ancestors were reduced to numbers like that, but if the genetics is right, the event that truly came closest to erasing our lineage from Earth happened long before the Toba supervolcano ever stirred, and it was not fire that nearly ended us. It was ice. When a population squeezes through a bottleneck like that, it isn't just the head count that changes. The DNA itself starts behaving differently. In a big, healthy population, natural selection has room to work. Picture a vast orchestra, hundreds of musicians, rows of violins, a forest of woodwinds and brass. If one violinist plays a slightly sour note, the overall sound barely changes. The orchestra can lose a clarinet here, gain a trumpet there, and the symphony still comes through. That's what genes are like in a large population. There's so much variation, so many copies of each gene, that random quirks mostly average out. Harmful mutations tend to be weeded out over time. Helpful ones, even if they start rare, can slowly spread as the individuals who carry them do a bit better and leave more descendants. Now shrink that orchestra. Take those hundreds of players and whittle them down to a string quartet. 2 violins, a viola, a cello. Suddenly, every instrument matters. One player leaving, or playing out of tune, can transform the music completely. A single missing part can't be hidden in the crowd because there is no crowd. That's what happens to a genome in a bottleneck. When numbers crash, you still have mutation and selection, but something else swells in importance: chance. Geneticists call it drift. Not because genes literally drift around, but because in a small population, the frequencies of gene variants, the different versions of a gene we call alleles, wander up and down the way pollen grains drift on a pond, not because they're better or worse, but because of who happens to have children and who doesn't. Imagine a generation of our bottleneck ancestors, a few dozen small groups scattered across shrinking habitats. Some individuals carry a slightly beneficial mutation, say, a tweak in a gene that helps them fight a particular parasite. Others don't. In a big population, that tiny advantage can, over many generations, build up. In a small population, that whole line might vanish in a bad year, not because the mutation failed, but because its carriers were in the wrong place when the drought hit. At the same time, mildly harmful mutations, ones that, in a large population would eventually be filtered out, can slip through. In a village-sized population, the difference between a bit less fit and a bit more fit is so small that random events can overwhelm it. The nearly neutral theory of evolution has a simple way of putting this. When effective population size is tiny, natural selection's grip loosens. Slightly damaging variants can behave almost like neutral passengers, drifting to higher and higher frequencies just by luck. Some of those passengers get off the bus after a few stops. Others ride all the way to fixation, becoming the only version of that gene in the entire population. From our vantage point, living nearly 1 million years later and reading the genomes of billions, we see the imprint of that process. Certain stretches of our DNA are strangely uniform, as if everyone is playing from the same narrow score. Other places are missing variants that, in a large stable population, you'd expect to see. The bottleneck wasn't just a pruning of branches, it was a rewriting of melodies. We can watch a version of this story in another species whose fate we know. On Wrangel Island, off the coast of Siberia, the last woolly mammoths hung on long after their mainland cousins were gone. Rising seas stranded a small group there perhaps 10 or 11,000 years ago, maybe a few hundred, maybe 1,000 animals at most. For thousands of years they survived. Generations of calves stumbling over the tundra, small herds moving between icy rivers and windswept hills. But all that time, they were living inside a genetic bottleneck. When scientists sequenced the DNA of one of those late Wrangel mammoths and compared it to a much older mainland mammoth, the differences were stark. The island mammoth had lost a big chunk of its genetic diversity, less heterozygosity, fewer mitochondrial lineages. Its genome was scattered with odd defects, deleted stretches, premature stop signals in genes, broken versions of proteins involved in smell, in fur texture, in chemical signals. It looked as if slightly harmful mutations had accumulated like rust on an old machine. Some researchers describe this as the early stages of a genomic meltdown. Not an instant collapse, but a slow accumulation of small problems, each one not lethal on its own, but together nudging the population closer to the edge. Others have argued that, even with this genetic burden, the Wrangel mammoths might have muddled through if an external shock hadn't finished them off. Either way, the pattern is clear. Long periods of small population size change the rules. Strongly harmful mutations can still be purged. If a calf inherits 2 copies of a lethal variant, it doesn't survive to reproduce. But the mild stuff, the almost okay variants, pile up. Now turn back to our ancestors in their deep Pleistocene bottleneck. Their situation wasn't identical. They likely lived in a more complex metapopulation, with groups splitting and rejoining, and they endured their low effective numbers for far longer than the Wrangel mammoths did. But the same basic forces were at work. Chance became a major architect. Some beneficial variants were simply lost when their carriers died childless. Some slightly harmful variants slid through, riding the bad years and the good, and became common. When the climate finally calmed and populations began to grow again, those changes came along for the ride. You carry the legacy of that in your own cells. Some geneticists suspect that parts of our immune system bear the marks of these ancient squeezes. The HLA genes, the ones that help your body recognize foreign invaders, are famously diverse, but that diversity is patchy. Certain variants are unusually common worldwide, as if a few lucky versions drifted through bottlenecks and then spread as populations expanded. Others are strangely rare or localized, perhaps because they arose after the worst bottlenecks were over, or because they were trimmed away in particular environments. Metabolic traits may tell a similar story. How you handle fats and sugars, how your body responds to famine and abundance. These are shaped by both selection and drift. A lineage that survives repeated starvation may, by chance and by selection, carry forward gene combinations that favor efficient storage, strong insulin responses, or resilience to certain plant toxins. Later, in a world of agriculture and supermarkets, those same combinations can become liabilities. Some researchers have even wondered whether aspects of our neurological wiring, our risk of certain disorders, the way our brains develop, might have been subtly shifted by ancient bottlenecks. Not in a grand, purposeful sense, but through the slow ratchet of drift and selection, acting on tiny populations, twisting and tuning neural genes over hundreds of thousands of years. These ideas are difficult to prove. They rely on demographic models, assumptions about how strong selection was, and patterns in present-day genomes. For now, they're educated possibilities rather than closed cases, but they highlight a deeper point. Bottlenecks don't only destroy, they also prepare. When a population shrinks, variation is lost. Many alternative genetic solutions to life's problems disappear forever. That sounds purely negative, and in many ways it is. Less raw material for evolution to work with means fewer options. Yet, in the strange arithmetic of evolution, a bottleneck can also act like that narrow channel we imagined earlier. A river forced tight between canyon walls. Pressure builds. Differences that do survive the squeeze, however they got there, become the starting points for everything that comes after. When the climate eased around 813,000 years ago, and habitats opened up again, the descendants of that tiny ancestral population began to spread. Not as a homogeneous wave, but as branching currents. Some stayed in Africa, others pushed into Europe and Western Asia, and others again into the vastness of the East. They all carried the same basic toolkit shaped during the bottleneck. The fused chromosome that distinguishes our lineage from other apes, a reduced but distinctive palette of gene variants, and whatever mix of beneficial and mildly harmful mutations chance had allowed to persist. From that constrained starting point, evolution could move quickly. New mutations appeared in growing populations, selection could once more sort more efficiently among them, and different environments favoured different solutions. What had been a single squeezed lineage began to fan out, eventually giving rise to Neanderthals, Denisovans, and much later, us. In that sense, a bottleneck is both a scar and a reset. It simplifies the genetic score, pares down the orchestra, and then, when the hall fills again, asks, what new music will you make with the instruments that remain? In the next part of our story, we'll follow those small, scattered bands of survivors as they step into a recovering world, and watch how their numbers and their possibilities begin to swell. Imagine that same small band we met near the eruption, not on the night the ash began to fall, but months later, maybe a year. Long enough that the terror has blurred at the edges, but not enough that anyone can forget. The sky's still wrong. Most days it's a hazy, muted grey, the sun a pale coin behind high dust. Shadows are soft, colours washed out. The air tastes faintly of stone. Sometimes, after a windy night, a thin film of grit coats the rocks, the sleeping skins, the children's hair. But something else is different now. The rains are trying to come back. Not the familiar storms of earlier years, but stuttering showers, irregular and cautious. For an hour the clouds open, and water patters on ash-dusted soil. Then the sky closes again, as if unsure. In the damp patches that linger, seeds that have waited for seasons, maybe decades, begin to stir. A few weeks later, the first green returns. Tiny shoots push up through grey. At first the band is afraid to trust it. They've watched plants wither in the strange light before, leaves crumbling to nothing under anemic sun. But some of these new shoots hold. Grasses take root in sheltered hollows. Tough shrubs send leaves from charcoal-black stems that survived the burn. Far away, in other valleys, on other coasts, other bands of humans are watching the same hesitant recovery. They don't know it, but they are part of the same fragile experiment, scattered pockets of our species, clinging on in a world still shuddering from catastrophe. They are not many. Geneticists, peering back through time with their models, don't see smooth, stable populations. They see dips and sways, long periods when effective population size may have been counted in tens of thousands, not millions. Some earlier reconstructions imagine that Toba itself slashed us down to just a few thousand survivors worldwide, maybe the size of a small town. More recent work paints a subtler picture. No clean global crash at exactly 74,000 years ago, but long-term small numbers, regional ups and downs, complex structure inside Africa. What is clear is that our ancestors were never a vast, invulnerable horde. They were always closer to the edge than we'd like to imagine. So how did the ones who made it through actually live? For some, the answer lay where the land meets the sea, on a stretch of coast that would one day be called South Africa. Waves rolled in as they had before the eruption. Tides rose and fell. In the shallows, mussels and limpets clung to rocks. Kelp forests swayed just offshore. Fish schooled in the dim water, oblivious to the drama unfolding on land. Here, in caves like those at Pinnacle Point, humans found a refuge. Archaeologists digging into those caves have uncovered layer upon layer of shell. Piles of discarded mollusk shells, meters thick in places packed with the chemistry of ancient meals. The dates of those layers stretch from around 170,000 years ago to well past the time of Toba. There is no sudden break, no obvious gap that screams everyone vanished. Instead, the record suggests continuity. People were there before the eruption, and people were there after, still gathering shellfish, still napping stone, still tending hearths. Coastal foraging offered something precious in an unstable world: reliability. Shellfish don't care about grasslands turning brown. They don't migrate away when inland herds disappear. As long as the tides continue, the intertidal zone produces. Even under a dimmed sun, even with cooler temperatures or disrupted rainfall, low trophic marine resources can remain stubbornly available. A band that knows how to read a rocky shoreline, when to prime mussels which pools hold fish at low tide, how to avoid rogue waves, carries, in its cultural memory, a survival kit for hard times. They didn't rely on shellfish alone. Inside those same South African caves you find evidence of fire carefully controlled, hearths rebuilt in the same spots over and over, stone tools whose raw material has been heat-treated, deliberately baked in hearths to improve its flaking properties, an innovation that speaks to planning and experimentation. You find the remains of hunted antelope and other mammals, showing that even in harsh periods people were tracking and ambushing large game. You find traces of ochre, iron-rich earth that some of these early humans scraped, ground, and possibly marked their bodies or tools with, a hint that symbolic thinking was already woven into their lives. Put all that together, and a pattern emerges. Survival wasn't just about having the right genes. It was about flexibility, being able to switch between hunting and gathering, between inland and coastal resources, being able to use fire not only for warmth and cooking, but as a tool to transform stone, clear vegetation, manage landscapes, being able to live in tight social groups where information could be shared, where the knowledge of which bay still had shellfish after a storm, or which root could be eaten when nothing else grew, could be passed from elder to child, not lost with a single death. At Dabba, in what is now northern India, another story of resilience is buried in the ground. Here, along an ancient river system, archaeologists have found stone tools scattered through sediments that include a thin layer of Toba ash. Below the ash, small sharp flakes and cores characteristic of a particular Middle Stone Age technology. Above the ash, more of the same. No dramatic shift, no disappearance. Whatever the eruption did to the landscape there, whatever ashfall and climate wobble came in its wake, humans adapted. They kept making tools in familiar ways, kept returning to that river corridor, kept going. Zoom out, and you see a patchwork. Some regions probably suffered greatly in the eruption's aftermath. Thick ash deposits, poisoned water, collapsed vegetation. Local populations might have crashed or vanished entirely, their tool traditions ending in a final layer of charcoal and stone. Other regions, especially those buffered by coasts or less affected by ash, offered something like continuity, a thread that could carry human culture through. From these threads, over tens of thousands of years, a tangled tapestry of populations formed across Africa. Not a single unified group, but many small, semi-isolated bands and regional clusters. They split and rejoined, exchanged mates and ideas, sometimes drifted apart for so long that their descendants today carry genetic signatures as different from each other as some modern populations are from Neanderthals. Geneticists see hints of this deep structure in African genomes now. Lineages that seem to have diverged more than 100,000 years ago. Branches whose roots likely reach back to the period around and after Toba. Some models even suggest ghost populations, groups that left no clear fossil trail, but whose DNA once flowed into the ancestors of particular African peoples. Each of those ancestral groups was experimenting with its own set of solutions. Some might have leaned heavily on coastlines, others on riverine fish, or forest resources, or specialized hunting of particular herds. Their stone tool traditions, while sharing broad themes, developed regional flavors. Their languages, if we could hear them, would almost certainly have been mutually incomprehensible, each an intricate system of sounds honed to local needs. From this fragmented mosaic, a new phase began around 60,000 to 70,000 years ago. Somewhere in Africa, likely not in a single cradle, but in networks of connected populations, a subset of Homo sapiens acquired the right combination of population size, technology, and social complexity to push outward. They followed coastlines and rivers northeastward, crossing the narrow straits into Arabia in small groups. Each crossing, each leap into a new habitat was its own mini bottleneck, a handful of families carrying only a sliver of the genetic diversity present back home. Their descendants would spread along the shores of the Indian Ocean into Southeast Asia, eventually reaching Australia. Others would turn north into the Levant and beyond into Eurasia. Along the way, they met other humans, Neanderthals in the Levant and Europe, Denisovans in parts of Asia, maybe other, more mysterious cousins in regions we haven't sampled yet. They didn't just compete, they mixed. Today, people outside Africa still carry 1 to 3% Neanderthal DNA. Populations in parts of Asia and Oceania carry Denisovan ancestry, including variants that help with life at high altitudes or with particular pathogens. The out-of-Africa expansion was not a simple replacement, it was an absorption, a knitting together of lineages that had been separate since that earlier, deeper bottleneck nearly 900,000 years before. And yet, for all this mixing, not every humankind survived. Homo erectus, which had roamed parts of Asia for well over 1 million years, disappears from the record. The Neanderthals, master survivors of Ice Age Europe, fade around 40,000 years ago. Denisovans persist in genetic echoes only. On Flores, the small-bodied Homo floresiensis vanishes. In the Philippines, the newly discovered Homo luzonensis leaves tantalizing bones, then silence. Our lineage made it through. Theirs did not. There is no guarantee in that outcome, no inevitability that Homo sapiens would be the ones to remain when the dust, literal and metaphorical, settled. A slightly different climate wobble, a different disease, a different migration pattern, and perhaps one of those other humans would be telling this story instead, in their own way. But we're the descendants of the bands that found refuges when the sky dimmed, the ones who learned to read coastlines and forests, to share food around a fire, to encode survival strategies in stories and symbols, the ones who, when the world pressed in, found enough room to keep going. From thousands of scattered bands, we arrived at billions. That jump can feel almost mythic, as if one day there were a few clusters of foragers on African coasts and riverbanks, and the next there were cities, satellites, endless streams of headlights moving across the night. But our DNA remembers the long in-between. When geneticists read the Y chromosome, the paternal line, and the autosomes, the great bulk of our genome, they don't see a smooth climb. They see a line that hugs the bottom of the graph for almost all of human history. Effective population sizes in the tens of thousands, maybe a few 100,000 at most, across the last couple of 100,000 years. Long epochs when our entire species could, in principle, have fit into a single modern megacity. Then suddenly, in the last 10,000 years or so, the line turns upward. It bends, then steepens, then almost goes vertical. Many lineages show 10-fold, 50-fold, even 100-fold growth in this brief window. In evolutionary terms, this is not a gentle tide, it's a tidal wave. To understand why, imagine again those small bands after Toba and after the deeper, older bottleneck. For tens of thousands of years they lived as hunter-gatherers, flexible, mobile, deeply attuned to landscapes. Their numbers did grow as climate stabilized and new territories opened, but slowly. A good year meant more children survived, but also more mouths to feed. A bad year, drought, disease, a failed migration of game, could erase a decade of growth in a single season. Then, in a few scattered regions, something new began to happen. People stopped just harvesting what nature happened to offer and started reshaping the living world on purpose. In a valley that would later be called part of the Fertile Crescent, small grains that humans had gathered for generations began to look a little different. Larger seeds, less shattering of the seed heads. Plants that, almost accidentally, did better when humans interfered, when they were trampled into the soil near camp, or dropped along paths, or cleared of competing weeds. At first, there was no sharp line between foraging and farming. Just a gradual shift, spending a little more time near patches of wild barley, burning a little more scrub to encourage the plants you like, returning to the same spots year after year because you know the harvest will be there. But slow experimentation adds up. Over generations, people learned that if you saved some seeds and scattered them deliberately, you could nudge the odds. If you weeded and watered, you could nudge them more. If you stayed put long enough, the land itself would begin to remember you. This was the beginning of agriculture. It didn't happen in just one place or all at once. Versions of it emerged independently in the Near East, in China with rice and millet, in New Guinea's highlands, in the Americas with maize and squash and potatoes, in Africa with sorghum and yams. Each case was its own long conversation between people and plants. The demographic consequences were profound. A field of grain can pack far more edible calories into a given area than a wild landscape. Domesticated animals, sheep, goats, cattle, pigs, gathered into herds added meat, milk, hides, and muscle power. Where a foraging band might need dozens or hundreds of square miles to support a few dozen people, a well-managed valley could support thousands. Birth rates rose. In mobile hunting groups, spacing children out made survival sense. It's hard to carry more than one very young child while tracking game. In villages, where food was stored and movement was limited, having babies closer together became possible. It also became necessary because life got paradoxically harder, even as numbers grew. The Neolithic demographic transition was not just more people, it was a new kind of struggle. Crowded villages meant human waste piled up, water sources became contaminated, and new diseases found fertile ground. Pathogens that couldn't sustain themselves in scattered bands could smoulder and spread in dense communities. Living alongside domesticated animals brought their microbes into our bodies. Measles, smallpox, influenza, Many of the classic crowd diseases that would later sweep cities trace their origins to this close cohabitation. Our genomes began to change again, but this time not because numbers were shrinking, because they were expanding. In dairying cultures, people who could digest lactose, the sugar in milk, into adulthood had an advantage. Milk was a clean, calorie-rich resource that could bridge bad harvests. Over a few thousand years, gene variants that allow lactase persistence spread like wildfire across parts of Europe, East Africa, and elsewhere, driven by the new diet. In farming populations eating more grains and fewer wild foods, selection nudged variants involved in starch digestion, in fat metabolism, in how we handle blood sugar. In crowded, pathogen-rich settlements, genes that offered even a tiny edge in resisting infections could mean the difference between a lineage that vanished in an epidemic and one that left many descendants. Unlike a bottleneck which randomly shaves away diversity and lets chance do much of the work, an expansion like this can sharpen selection. When there are more births, there is more room for beneficial mutations to appear and spread. Our DNA from the last 10,000 years carries hundreds, maybe thousands, of these small but telling changes. All the while, the head count climbed. 10,000 years ago, near the dawn of agriculture, there may have been only a few million Homo sapiens on the entire planet. That is less than the population of some modern cities. By around the year 1 CE, we might be talking about a couple of 100 million. By 1800, roughly 1 billion. By the early 21st century, over 8 billion. In just the span between your great-grandparents and you, the global population has multiplied several times. The curve is almost exponential, an explosion no less dramatic than any volcanic plume, only made of people. With this growth came something new in human experience. Cities, not just villages or seasonal aggregation sites, but permanent, densely packed urban centres, places where tens of thousands, then hundreds of thousands, and eventually millions of individuals lived stacked above and beside one another, sharing food and water systems, laws, stories, and pathogens. Urban life brought its own selection pressures and cultural innovations, sanitation systems, writing, money, bureaucracies, organised religion, standing armies. Each of these changed who survived, who prospered, who had children, who did not. From a genetic perspective, though, there's a quiet irony behind all this multiplication. We remain, as a species, strangely uniform. When you compare the genomes of two random humans from different continents, you typically find they differ at fewer than one base in 1,000. That might sound like a lot, but set us beside other great apes and the contrast sharpens. Some chimpanzee and gorilla populations have 2 or 3 times our level of genetic variability. Even some endangered apes with tiny modern ranges carry more diversity than the 7+ billion humans walking the earth. This is the shadow of those ancient narrows. Our numbers today tell one story, of expansion, of success, of ecological dominance. Our low diversity tells another, of long periods when we teetered near the edge, when a drought or epidemic in the wrong valley might have rewritten the future. You can see similar patterns in other species that nearly didn't make it. Cheetahs, for example, are so genetically uniform that skin grafts between unrelated individuals are sometimes accepted as if they were from the same animal. Their ancestors seem to have passed through one or more severe bottlenecks, possibly linked to past climate swings or habitat loss. Today's cheetahs carry that history and increased vulnerability to disease and reproductive issues. Northern elephant seals were hunted down to perhaps a few dozen survivors on a single island in the 19th century. Protection allowed their numbers to rebound to well over 100,000 now, yet their genomes still bear the stamp of that crash, reduced variation, long stretches where both copies of a gene are identical. European bison, decimated by centuries of hunting and habitat loss, survived only in zoos and a few reserves before being reintroduced to the wild. Modern herds, though numerically healthy, are genetically narrow. Their future resilience depends not just on how many there are, but on how much variation they carry. We are like them and unlike them. Like them, in that we have passed through our own genetic pinch points, and those events still whisper in our DNA. Unlike them, in that our recent expansion has given us an unprecedented power to alter the world that once threatened us. We have become a geological force. We dig and blast and tunnel more rock each year than many volcanic episodes move in their lifetimes. We pump greenhouse gases into the atmosphere, shift river courses, level forests, spread species across continents, and drive others to extinction. The carbon we release rivals in its climatic impact some of the great natural perturbations of the deep past. Once, a supervolcano in Sumatra could darken the skies and make our scattered ancestors cling to coasts and caves. Now, their descendants light up the planet at night. From orbit, the glow of human settlements traces coastlines and rivers, throws sharp constellations of cities across what were once empty plains. And yet, in every one of those lights, the same old story burns. A genome shaped by small numbers and close calls. A species whose success is built on fragility and chance. A line that could easily have broken, now looping itself around the planet, asking, perhaps for the first time on this scale, not just how we survived the past, but what we will do to shape the future. The lake that hides the Toba caldera lies quiet now. Its waters mirror the sky that once turned strange. Around its shores, people live ordinary lives, fishing, farming, telling stories. The supervolcano sleeps, but the descendants of those who outlived it do not. Today, if you travel to Sumatra and stand on the rim of that ancient wound, it doesn't look like the end of the world. It looks like a postcard. Lake Toba stretches out below you, a sheet of deep blue water almost 100 kilometers long, held in a bowl of green mountains. The lake's surface lies nearly a kilometer above sea level, cool and misty in the mornings, the air smelling of wet earth and wood smoke. Terraced hillsides step down toward the shore, patched with fields and fruit trees. Villages sit at the water's edge, boats pulled up on narrow beaches, their hulls reflecting in the calm. In the middle of it all rises Samosir Island, an island inside a lake inside a volcano. It isn't a small speck of land. It's a block of uplifted caldera floor the size of a small country, ringed by cliffs and gentle slopes, ridges and bays. From the waterline up to the crest, it's wrapped in tropical vegetation, banana plants, pine trees, coffee bushes, flowers that open and close with the light. At night, the crater that once glowed with incandescent magma is dark and quiet. A few scattered house lights blink along the shore. Somewhere a motorbike passes on a winding road, its sound fading quickly into the surrounding forest. If you didn't know, you'd never guess you were standing inside one of the largest explosive scars on the planet. The lake you're looking at is not just big. It's the biggest volcanic lake on Earth, covering more than 1,000 square kilometers, with depths that plunge to about 500 meters. All of that water, every reflection and ripple, rests in a hollow excavated by the youngest Toba eruption, roughly 74,000 years ago. Where superheated ash once roared upward to the stratosphere, there is now a cool body of fresh water, home to fish, plankton, and someone's morning swim. Around the lake live the Batak people, especially the Toba Bag, whose ancestors have called these shores home for centuries. Walk through a lakeside village and you see their architecture immediately. Long wooden houses with steeply gabled roofs curving upward at the ends, like boats turned skyward. Some are brightly painted with geometric designs and stylized animal motifs. Others are weathered to a silver grey, their beams darkened by smoke from decades of cooking fires. Many Batak today are Christian, the legacy of missionary work in the 19th and 20th centuries. Churches with crosses rise among rice fields and clove trees, yet older traditions still pulse quietly beneath the surface. Ancestor veneration, ritual songs, a sense that the land and the spirits who inhabit it are part of the same extended kin network as living relatives. Grave monuments stand on hillsides overlooking the water, elaborate stone or carved wooden structures marking the resting places of important ancestors. They face the lake that filled the volcano, as if even in death the Batak remain in conversation with the landscape that made them. Children play on the shore. Fishermen cast nets from small wooden boats, their silhouettes stark against the afternoon sun. Tourists take ferries across to Samosir, sit in cafes, watch the clouds build over the crater rim. The mood is tranquil, almost sleepy. It's hard to reconcile that peace with what happened here. That is the great geological irony of Toba. The same eruption that carved out this basin was, by most measures, one of the most violent events the planet has seen in the last 25 million years. Thousands of cubic kilometers of rock were pulverized and thrown into the air. Ash clouds spread across continents. Magma chambers that had been building for hundreds of thousands of years collapsed in a geological instant. Now, the scar is a place of rest. Forests drape the caldera walls. Birds weave through the canopy. People farm the slopes, their fields following lines drawn by ancient fractures and landslides. Life has not just returned, it has flourished, layering green over grey, culture over catastrophe. In that way, Toba's story mirrors our own. Our species too passed through fire and narrowness, and came out the other side changed. Not from this eruption alone, and not as simply as the old catastrophe stories once claimed, but through a long sequence of climatic swings, near misses, and slow recoveries. The caldera filled with water. Our population graphs bent upward. The world that almost lost us now teems with our descendants, but the volcano under Lake Toba has not retired. If you go to certain coves along the shore, you can bathe in hot springs that bubble up from below, water warmed by residual heat deep in the crust. Fumaroles vent gases through cracks. Small earthquakes rattle the region from time to time, gentle reminders that the system beneath is still alive. Geologists map the caldera edges, measure ground deformation with satellites, lower instruments into the lake to sample temperature and chemistry at different depths. They track seismic waves, watching for patterns that might indicate magma or fluids moving underground. They don't see signs of an imminent eruption. There is no swelling dome about to burst, no vast chamber obviously filling with fresh melt. On human timescales, Toba is quiet. On geological timescales, it's simply between acts. A true repeat of a VEI-8. Toba-scale supereruption in our lifetimes is considered extremely unlikely. The rough probabilities, based on sparse records and a handful of known supereruptions worldwide, are tiny, fractions of a percent over many centuries. And yet, the lake sits where it sits because such an eruption has already happened once. History in deep time is not an ironclad schedule, but it is a proof of possibility. Toba is not alone. Half a world away, beneath the forests and geysers of Yellowstone, lies another giant caldera system. To most visitors, Yellowstone is a wonderland of hot springs, steaming vents, and grazing bison. To geologists, it is also a supervolcano that has produced multiple caldera-forming eruptions over the last few million years. The US Geological Survey monitors it closely and estimates the chance of another supereruption there in any given year at around 1 in 700,000, vanishingly small, but not zero. In Italy, near Naples, a broad low bowl called Campi Flegrei, the burning fields, hints at another restless giant. Towns, roads and harbours sit right inside the caldera. Ground there has been rising and falling in slow pulses for decades, accompanied by swarms of small earthquakes. Scientists at Italy's monitoring agencies analyze each twitch and tremor, balancing the need for vigilance against the reality that unrest does not always culminate in disaster. In New Zealand, the Taupo volcanic zone holds yet another super-eruption scar beneath lakes and rolling hills. Around the Pacific and beyond, there are others, less famous but no less real. These systems remind us that the interior of the Earth runs on its own timetable. Magma accumulates over tens or hundreds of thousands of years. Pressure builds and releases in complex ways. Nothing about this process is tuned to human calendars or to our sense of what would be convenient. We live here anyway. We build homes on caldera rims, plant vineyards in ash-rich soils, soak in hot springs that are, in the most literal sense, heat leaking from the deep. We fly jets through skies that, very rarely but not never, can be filled with ash from eruptions large enough to circle the globe. In that sense, the story of Toba and of all supervolcanoes is the story of a planet of cycles, eruptions and recoveries, ice ages and thaws, genetic bottlenecks and population booms, extinctions that wipe the slate, and radiations that redraw the tree of life. Nothing in this system is permanent, not the quiet surface of a lake, not the apparent stability of a climate, not even the dominance of a particular species. What persists is change itself, the slow, relentless turning of the Earth's internal and external gears. And yet, threaded through that impermanence is something else, resilience. The caldera that once glowed with molten rock now holds clear water and fishing boats. Forests have rooted in ash. Human languages echo off walls carved by pyroclastic flows. The Batak build houses and sing songs in the shadow of a volcano that could, in some unimaginably distant future, wake again. You, listening to this, carry your own version of that paradox. Inside each of your cells, coiled into the chromosomes you inherited from your parents, are traces of all those earlier narrowings and expansions. Your genome bears the mark of the old deep bottleneck 800,000 or 900,000 years ago, the long epoch when our lineage's effective population size hovered near the edge. It carries signatures of migrations, of mixing between branches once called separate species, of diseases weathered, diets adopted, climates endured. You are, in a very literal biological sense, a descendant of survivors. Not just of Toba's ash and aftermath, which our best evidence now suggests was harsh, but not the singular apocalypse once imagined, but of countless other crises, droughts that erased valleys from memory, epidemics that burned through camps and cities, local eruptions whose names we no longer know. Each time, somewhere, some cluster of people made it through the Narrows. Their children had children. The line continued eventually to you. When you picture Lake Toba, its calm surface, its forested rim, its island rising from within, remember that it is both a memorial and a promise, a memorial to the scale of forces that have shaped life on Earth, indifferent to our plans, a promise that recovery is possible, that from even the